All right, today we are going to start on chemical bonding and we are going to focus on covalent bonding. What we are going to cover today will be drawing of the Lewis structures and using the Lewis structure to predict the shapes as well as the bond angle using the VSEPR model. So if you are looking at your chemistry notes, we are going to cover things like 2.2.1, 2.2.4, as well as all the drawing of the covalent compound. So if you turn to the next page here, this gives you an overview of chem bonding. So if you look at the chem bonding part, majority is about the covalent compound. So ionic compound and metallic bonding has been covered in the Quizit HBL assignment, one of the assignments that I have done on Quizit. So for covalent bonding wise, this is divided into two parts. We have simple molecules as well as we have a giant covalent structure over here. So today we are going to focus on the simple molecules because from the drawing of the simple molecules, it allows us to predict the shapes, which will then affect the type of bonding. So when you predict the shape of the molecules, then you will be able to predict things called polarity and the intermolecular force. So for most students who struggle with chemical bonding, covalent bonding, their main concern is they are unable to draw the Lewis structures. And because of drawing the wrong structures, and therefore they result in the wrong shapes and wrong choice of polarity or non-polar, and therefore affecting the intermolecular forces choices. Okay, so today we are focused on just getting the drawing and the shapes correct. So we will turn to page 8, which starts on covalent bond. Now, how do we know whether something is a covalent bond? It's going to form covalent bond. Generally, in the past, we look at between non-matters. So if I have two non-matters and the two non-matters form a bond, they will tend to share a pair of electrons, and covalent bond is the electrostatic forces of attraction between that shared pair of shared pair of electrons and the positive nuclei of the atoms. So it's generally between non-matter atoms. So for example, H and Cl, N and O, C and O. All right. Now, however, there are also covalent compounds that is formed between matters and non-matters. There are also that. Okay, so what are those matters that will tend to form covalent compound with non-matter atoms? So how do we know whether it will be covalent or ionic? Right? So in order for us to do so, I will have to bring your attention to the data booklet. So if you look at the data booklet that is in your notebook, you have turned to this table. And this table over here, table 9, has all the electronegativity values of the elements. So you see all these numbers below, these are the electronegativity values. So what you will do is that, let's say, if I have beryllium bonding with fluoride or beryllium bonding with bromine, so I will take note of what is bromine's electronegativity value, and I will take note of what is beryllium's electronegativity value. And what do? We will do two calculations. First, we will find the difference. And in this case, it will be 3.0 minus 1.6. So I get a 1.4. And then we also get the average. The average will be 3.0 plus 1.6 divided by 2. So it will be about 2.3. Okay, so knowing the difference and the average 1.4, 2.3, what do you do is that you will go on to this diagram. Okay, on table 17. So if you still remember, our difference was 1.4, our average is 2.3. And using this triangle bonding diagram, you look for roughly 1.4 on the different side, and you look for 2.3 for the average side, and you connect them together. And you see roughly which region do they fall in for under. Okay, it's an estimation. It's an estimation, not drawn to scale. Okay, so roughly that. That is one way that you can do so, is to use this triangle bonding diagram. Okay, another way that you can do so to know whether something is going to be an ionic or covalent, if you are having a matter and non-matter, if you don't want to use the triangle bonding diagram, another possibility is to look at the electronegativity difference. Generally, if the electronegativity difference is less than 1.8, then it is a covalent compound. So anything 1.8 or higher, generally it will be an ionic compound for the delta En. And for delta En in this case, which is 1.4 and is not 1.8 or higher, then it is likely to be a covalent compound. So there's actually two ways. Both ways uses electronegativity. First way, just look at using this triangle bonding diagram where you work out the electronegativity difference and the average, and you try to match which section of the triangle bonding diagram it falls under. Another way is just to look at delta En difference, okay? And any delta En less than 1.8 will not be an ionic compound. All right, so that's how you can work out, because now we are having, besides non-metals and non-metals atoms bonding together, we can have metals and non-metals atoms bonding together, and they are classified under covalent compounds. So we will have to do the classification first. Okay, so if after classifying you find that it is really a covalent compound, then between them, what they will be forming will be covalent bond. That means they are going to share a pair of electrons, and the bond is formed because of the attraction between the nucleus as well as the shared pair of electrons. So for example, IH and Cl, and if they do share a pair of electrons, the nucleus is positively charged and the electrons are negatively charged. So in between them, they will form electrostatic forces of attraction. So take note, usually difference of electronegativity less than 1.8 or equal to 1.8. Now, why do they form bonds? When they form bonds, they try to achieve the stable noble gas configuration, or they try to get an octet configuration or a stable noble gas configuration. Okay, so there are two ways that they can form bonds, form covalent bonds. The first way is the usual normal covalent bond ways, which is each atom will contribute one electron for sharing. So for example, in HCl, H will contribute one electron and Cl may contribute one electron for sharing. And in this way, they form a normal covalent bond. Now, there's also things known as coordination bond. It is also a form of covalent bond, but just that both the electrons in the covalent bond comes from one atom, and the other atom is contributing none. All right, an example of that would be something like this. If I have ammonia, and if it reacts with H+, now H+ being a cation, it has no electron. So between ammonia and H+, in order for them to form ammonium ion that looks like this, there's a covalent bond that is going to be formed. All right, and the covalent bond that is going to be formed is a dative covalent bond. And how do we know that it's a dative covalent bond? Because both the electrons that is used for sharing over here all originate from the nitrogen atom. And the hydrogen ion here is not sharing any electrons. But at the end of the day, we are still seeing a shared pair of electrons being shared between two non-metal atoms. So therefore, it is a covalent bond because they are still sharing electrons. But just that these electrons The electrons originate from the same atom. So we call this a coordination covalent bond for the second case. Now, is there a difference? Can we tell a coordination covalent bond from a normal covalent bond in terms of its bond strength, in terms of its reactivity? You'll find that no, a normal covalent bond and a coordination covalent bond has the same bond strength, has the same properties. It's just that the way they are formed is a bit different. Now, moving on, we know that all the atoms try to attain the stable noble gas configuration by sharing electrons in covalent bond cases. So we are going to draw covalent bonds using Lewis structure. So what's the difference between Lewis structure and dot and cross? Is that Lewis structure, we usually shows electrons using lines. So we show electrons using lines or dots, but definitely no crosses. Okay? So as we are drawing our Lewis structure, to describe the electrons, there are two terms, mainly bond pair and lone pair. So bond pairs are the electrons that's used for sharing between the two atoms, while lone pairs are electrons not participating in the bonding. So they are not being shared. All right. Now, there is actually a proper way to draw Lewis structure. But I think most of the time, most of our students are drawing Lewis structure by their feeling. Okay, so actually it's not correct. I'll show you how to draw Lewis structure going through the steps. Okay. So to draw Lewis structure, what do we do first is to count electrons. So for example, maybe I don't draw ammonia. I may draw PCl3. Okay. So following the formula, what we will usually do is that we will place the less electronegative atom in the center. So when we place the less electronegative atom in the center as the central atom, okay, so in this case, you can refer to the electronegativity values, or after a while you more or less get it. All right, we place the less electronegative atom in the center, except when it's hydrogen. Okay, for hydrogen, you will never place it in the center because hydrogen can only form one bond. So once you place it in the center, it forms one bond and that's it. You can't bond anymore. So for in this case, our phosphorus is less electronegative than chlorine. So we will place the phosphorus in the center. Second, we will count electrons. Phosphorus being from group 15, it has 5 valence electrons. Chlorine from group 17, it has 7 valence electrons, and I have 3 of the chlorine. So that gives me 21. So altogether, I need to draw a structure that has 26 electrons. So what do I do? So you can spread out the P and the Cl. In between them, at least form a bond, right? So you at least draw lines to form the bond between the central atom and the other atoms. Next, what do we do is that we take care of the surrounding atoms. We do not try to take care of all the atoms. So our focus will be to ensure that the surrounding atoms, in this case, will be chlorine, okay? Ensure that they have a stable electronic configuration. So in this case, we will try to make it an octet. So by placing electrons around the chlorine, one line refers to 2 electrons. So 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. So how many electrons have I drawn? So now you do your counting. So I have drawn 24 electrons. So what do? Is that we subtract the electrons from the total electrons. So I've drawn 24. So I use 26 minus 24. I'm left with 2. And what do I do with the 2 electrons? So you subtract the electrons from total. Any excess electrons usually we place on the central atom. So I have excess 2, I'll place on the central atom here. Okay, so that's how we get the structure first. But of course, is that all? No, we can check. So what are the things that we need to check? We need to check that we have octet for all the atoms. In this case, chlorine has all the octet and phosphorus has also an octet configuration. All right. So now some of the questions will be, when do we do double bonds? We do double bonds when there's not enough electrons to give every atom an octet or stable electronic configuration. And none of the atoms are allowed to have less than an octet. Then we will do double bonds. All right. So after drawing, you check for an octet for all the atoms or check for a stable electronic configuration for all the atoms. And you'll find that sometimes you do not get. So does it mean that your structure is wrong? Okay. So it may not be wrong because there are situations whereby the atoms are allowed to disobey the octet rule. So under what situation will the atoms be allowed to have disobey the octet rule? Let's turn to page 12. Under this three situation. First situation, this is a case whereby the molecules, the central atoms have lesser than 8 electrons and it's okay. And you'll find that usually they are the group 2 and group 13 elements. Change it to 13. So it's group for the group 2 and the group 13 elements. It is fine for them to have less than an octet. So if you find that after drawing, you find that they have less than an octet, you don't need to try multiple bonds to make it an octet. It's not necessary. Because for group 2 and group 13 elements, it's fine for them to have less than an octet. Why? Because a group 2 element has 2 valence electrons. Group 13 has 3. So you think about it, 2 electrons, you use all for bonding, so 2 times 2, your maximum get 4 only. And if you have group 13, you have 3 valence electrons. Everyone, you use all of them to form bonds, so 3 times 2, you maximum get 6 electrons. So you'll find that you're not getting 8, and it's quite normal, right? So if you have lesser than 8 electrons, before you try multiple bonds or before you say that your structure is wrong, check whether they are group 2 and 13 element in the central atom. If they are, then your structure is correct if they have less than an octet. So beryllium and boron, which is from group 2 and group 13, they then tend to form covalent compounds, even though we classify them as metals. All right, so based on that, you will find that after bonding, they tend to have less than an octet number of electrons. And that electron division is fine for group 2 and 13. But however, because we know that they are electron deficient, they tend to be very reactive. So given a chance, if they are near other compounds or near other atoms that can form bonds with them to allow them to get an octet configuration, they will react with those compounds. All right, so it's very common for BF3 and BeCl2 to undergo further reactions with other compounds to achieve an octet arrangement. So this is one exception whereby the central atom will have less than 8. Now, the next exception whereby the central atom may have less than 8 and in fact has an odd number of electrons, which we call it as radical. Okay, radical means something like this. You have an unpaired electron. And getting this unpaired electron with a structure less than 8 is very common for nitrogen. So for nitrogen, because nitrogen has 5 valence electrons, and nitrogen is not able to accommodate beyond 8 electrons, So you'll find that for nitrogen, it's quite common for it to have less than 8, such as it has 7 valence electrons, and it has an odd one that is unpaired, which we call radical. All right. So do you need to try to form multiple bonds to make sure that nitrogen has 8 electrons? You'll find that you can't do it. If you try to form multiple bonds and make it try to get 8, sometimes it doesn't work for nitrogen because it cannot exceed 8. And when you try to form another bond with it, you'll find that, or you try to find and form another double bond with it, it doesn't work. And it tends to be more stable with 7 electrons and as a radical. Okay? So example, let me show you a structure. So this is NO2. So in NO2, it's like this. Sorry, this is a radical, unpaired electron. So we represent the unpaired electron with a dot instead of a line. A line is a lone pair, it's a pair of electrons. A dot is one single electron. So if you look at this, then you'll find that nitrogen has 7 electrons. So some students will ask, then can we do this? Can we do this? We can't do this because nitrogen is group 5, oxygen is group 6 times 2. So total, your structure has 17 electrons. But if you look at what you have drawn 2, 4, 6, 8, 10, 12, 14, 16 electron. That is a leftover of 1. Then if what you're going to do with that, you're going to put here. And if you put it here, you'll find that this nitrogen now has 9 electrons, which exceed octet. So it has 9 electrons and it's exceeding octet, which is not allowed because it's a period 2 elements. Okay, why period 2 elements you can't have more than 8 electrons? Because if you remember your atomic structure, period 2 has orbitals 2s, 2p, 2s2, 2p, 6. That's the maximum that you can put into period 2. So it can hold only a maximum of 8 electrons. So where will your 9th electron go? Right? You don't have any 3s2 orbital because it's a period 2 element. So period 2 ends off with 1s, 2s, 2p. That's it. Right? So 2s and 2p can only hold 8 electrons. So you are unable to hold a 9th electron. So therefore, this structure will be wrong. Therefore, the best that nitrogen can is to achieve this structure, which has less than 8, so that it can occupy 2s2, 2p6 within this limit, and it will end up as a radical. Okay, now is radical stable? Is radical stable? Just like is this stable? You'll find that this is not stable, right? Because it has 2, 4, 6 electrons. It has 2, 4, it's not a stable configuration. So given any chance, it will quickly react with something to get an octet or stable configuration. So same for this. Is NO2 stable? So NO2 in this structure, which is a radical as an unpaired electron and less than an octet, is highly reactive. So it can exist as NO2, but if there's another NO2 around, what will happen is that they will take a bond, they will form a bond. So this radical and this radical here will bond and form N2O4. So when you form N2O4, you will find that now it has electrons 2, 4, 6, 8. Much better, right? So the idea here I was trying to tell you is that for nitrogen compounds, it is quite common for them to have less than an octet, and it's quite common for them to be a radical. That means it consists of an unpaired electron. All right, that's the is Lewis structure. But of course, we know it's not very stable. So given a chance, they may combine the two NO2 molecules, or the two NO molecules may combine and give you N2O4 or N2O2. Okay, so these are the two rules that we can see. So in cases which are less than an octet, so if you happen to draw a structure that's less than an octet, just check whether it's group 2, group 13, or is it a nitrogen compound. All right. Now, if it is, then it's fine. If it's not group 2, it's not group 3, 13, it is not nitrogen, and you have less than an octet, that means you have to try multiple bonds. Okay? Okay, so let's try two structure here, okay? For example, CO2. C is group 4, 14, so 4 valence electron. O, 6 times 2, so 12. So you have your 16 electrons. So most of the time, oxygen needs to form 2 bonds because it's short of 2 to get an octet. So most of the time, we do a double bond for oxygen. Take care of the surrounding atoms to make sure that they have an octet. And then count how many electrons you have drawn. So 8 and 8, I've drawn 16. So there's none left over, and therefore this is the structure. Before we say that this is the structure, double check central atom. Does it have an octet? Okay. And same for this structure, C2H, for example, nitrogen. Nitrogen is group 5. So 5 times 2, we have only 10 electrons. If I allow nitrogen to form only one bond, it may not be enough because it needs 3 more electrons to reach 8. So if we try triple bond, so that they get 3 electrons from sharing, and then we put in the electrons so that all the atoms has an octet configuration, and we double check 2, 4, 6, 8, 10. Are we drawing the maximum allowed electrons? Yeah, 10. So this is the structure of NO2. All right, I will give you more structures to practice later. All right. Oh, let me draw H2O. H2O, very simple, right? Oxygen is group 6. Hydrogen will be 1 electron times 2. So total, I have 8 electrons in my diagram. So oxygen in the center, because we can never place hydrogen in the center. And then between them, at least a bond. For hydrogen, we don't look for octet, we look for duplex and duplex. So I have drawn 4 electrons, so minus 4, I left with 4. And what do I do with this? I will put on the central atom. And after that, I double check whether this has an octet. 2, 4, 6, 8. All right, that's how you draw your Lewis structure for atoms. Now, what about ions? If you have an ion, whether it's a polyatomic ion or a molecular ion, what will happen is that sometimes they carry charges, right? You may have positive charge, negative charges. So if you have a positive charge as a cation, what do? You have to lose an electron. And who do you get the electron from? You lose an electron from the less electronegative atom. Now, if you do not know which is less electronegative, again, go to data booklet. There's this electronegativity periodic table that shows electronegativity values. Now, if you have an anion, that means you have to gain one more extra electron. And who do you give the electron to? You actually give the electron to the more electronegative atom. So in this compound, like NO2, there's covalent bond, but it is charged. So for example, if I place a NO2 plus with a Cl minus, I would say that between the plus and minus is ionic bonding. But within the NO2 itself, there is covalent bonding. All right. Okay. So it's the same like other salts like ammonium sulfate or ammonium carbonate. So in the ammonium, it has a positive charge and we have negative charge. So between oppositely charged ions, its attraction is ionic. But within the NH4, because these are non-metals, within the CO3, because these are non-metals, there will be covalent bonds. So this structure has both covalent and ionic bonding. All right. So let's see how do we draw NO2 plus and CH3 plus minus. So same thing, NO2 plus, N from group 5, O from group 16, so 6 valence electrons times 2, so I have 12. Now I have to minus an electron from the less electronegative atom, so I minus from nitrogen. So I have something like this, total 16 electrons. All right, so nitrogen is less electronegative, so we subtract electron from it. Now, place the less electronegative atom in the center as surrounded by oxygen. So maybe we will want to try double bond with oxygen. Since we know oxygen needs 2 more electrons to get octet, so maybe we try something like this first. So after trying, how many electrons have I drawn? I've drawn 8 and 8, 16. I'm left with 0. So nothing to place on nitrogen. And then I complete it by putting in a square bracket and a charge. So now let's check. Does nitrogen has an octet configuration? If yes, then okay. If less than an octet, also still okay because it may be a radical, remember? All right. But if more than an octet, definitely wrong. Okay. Now, next, let's look at CH3 minus. In CH3 minus, C has 4 electrons. H, there are 3 of them, so 3 times 1, so 3. Now, the extra electron should go to the more electronegative atom, which is, I think, the carbon. So carbon will have more electron added because it's more electronegative. So I will have 5 and 3, 8. So draw your C. Remember, hydrogen cannot be in the center. All right. And between them, at least form a bond. Hydrogen, we look for duplex. And that's it. Right? And then what do? I finished my drawing. I've drawn 6. So I minus 6. I'm left with 2. What do I do with them? I put on the central atom. And I end off with a square bracket minus. So check your hydrogen. It has a duplex. Check your carbon. It has a stable octet configuration. And you have used up all your 8 electrons. So this is the structure with a negative charge for the for the anion. All right. So once you finish your drawing, what do we do to the structures? How does the structures help us to determine the shape? So once we finish the drawing, now we are going to apply our VSEPR theory to determine the shape. So where is VSEPR? Can you turn to page 17 of your notes? Okay, so after you finish a Lewis structure, you always, most of the time, will apply your VSEPR to find out the shape and the angle. So what is VSEPR? Okay, it stands for valence shell electron pair repulsion theory. So this theory states that the electrons regions will arrange themselves in such a way that they will be as far apart as possible to reduce electron repulsion. So when we say electron regions, this could be regions of bond pairs. This could be regions of lone pairs. This could be regions of unpaired electrons, radicals. Understand? So all these are electron regions. And all of them will try to adopt an arrangement to make them as far as possible so that they will minimize electron-electron repulsion. Okay? So in order for us to know how to arrange it, what do is that we always count electron regions around an atom. which atom is always the central atom. Okay, so finish with our drawing. If you still remember, let's say you have done your drawing over here. So what do we do to this drawing? We will count how many electron regions around the central oxygen. So 1 region, 2 region, 3 region, 4 region. So water, the oxygen has 4 electron regions. Okay, and out of the 4 electron regions, we have 2 bond pairs and 2 lone pairs. So we need to know how many regions in order for us to apply the VSEPR theory. All right, what about if it's a double bond? If it's a double bond, like in this case, it's still counted as 1 region. Okay, so that's why count as region. So this double bond is in 1 region and 1 region. So in this case, for CO2, there's 2 electron regions. And we are seeing 2 bond pairs. All right. So let's say if I have ammonia will look like this. So ammonia will have a region of 1, 2, 3, 4. 4 electron regions. Out of the 4 electron regions, 3 bond pairs and 1 lone pair. So we are going to first count the regions. Knowing that how many regions there are, what do we do is that after you have drawn your dot and cross diagram, now we are on page 17. Okay, after we have drawn your dot and cross diagram, we count the electron regions around the central atom. So you may want to change the pairs to regions, because I find that regions is easier for students to understand. So count electron regions. A single bond, a double bond, a triple bond, whether it's a coordinate bond, is still counted as 1 electron region. A lone pair is also counted as a 1 electron region. Same, a radical is also counted as 1 electron region. So after we know how many electrons regions are there, what do we do is that we will first determine the electron geometry. All right, so that is the so-called the basic shape. We don't call it the basic shape. So we will use it to determine the electron geometry. Maybe you want to change it to electron geometry. So determine the electron geometry first. And the electron geometry will give us an idea how to arrange the electron regions. Okay, so in this case, let's say sulfur, it has 1 region, 2 region, 3 region, 4 region. So I will make use of 4 to find out its electron geometry first. Okay, then only after you have the electron geometry, then you determine the actual shape. The actual shape is known as the molecular geometry. All right, it's the molecular geometry. It's what you actually see. All right, the electron geometry is how the electron regions are arranged. The molecular geometry is how the atom looks like to you, its actual shape. Understand? All right. And then, of course, sometimes they may want you to determine the bond angle. And the bond angle is actually starts off from the electron geometry. So we use the electron geometry as a basis to start off the bond angle, and then we slightly make some modifications to the angle. All right, okay, let me show you how to do it. So for example here, so NH3. So first thing, you draw the dot and cross. Second thing, you will count the electron geometry, or count the electron domains, or count the electron regions. So I have 1 region, 2 region, 3 region, 4 region. So with the 4 regions in mind, okay, 4 electron regions in mind, I will then now determine the electron geometry. All right. How do you find the electron geometry? You will go to this table here and you look at this part. All right. Look at this part to determine the electron geometry. For SL students, you only need to learn 2 electron regions, 3 electron regions, 4 electron regions. That's all. So you will use it to determine the electron geometry. So back to that, I have 4 electron regions. So I have 4 electron geometry. So it's telling me that arrange the 4 electron regions in this tetrahedral shape in this arrangement so that you will reduce repulsion. So if I follow what they tell me, then I will arrange my nitrogen in this manner, 4 electron regions. And then this region is a H, this is a H, this is a H, and this is a lone pair. Right? Now, so this is the electron geometry. So electron geometry is tetrahedral, and they say that as long as it's tetrahedral, it gives me an angle 109.5. So this angle here is a starting angle that I will use for modification later. So I know that, okay, now the angle is, I must start off from 109.5 first. Okay, next, I will determine the actual shape. The actual shape is known as the molecular geometry. So how do I know what's the actual shape? You take a finger and cover up the lone pair because you are not able to see electrons. They are so tiny. So you imagine that you cover up this, and what will your eyes see? Your eyes will be seeing something like this because you are not able to see this electron. So you'll be seeing something like this as a structure. And that is the molecular geometry or the shape. So what you see is the shape. So I'm going to see something like this, a triangle kind of pyramid. So therefore, the name is trigonal pyramida. So we get the shape after we hide the lone pair. So from this structure, if I hide that lone pair and I don't see this, I will be seeing a triangle pyramid. So that's the molecular shape. The shape is triangle pyramidal, right? Now, then I'm going to look at the bond angle. Before I look at the bond angle, I know I start off from 109.5 because the electron geometry says so. Right? So how do I adjust the bond angle, and why must I adjust the bond angle? It's because of this portion here. Now, we have 2 types of electrons. One of them is called lone pair. One of them is called bond pair, right? And we find that lone pair, because it's not localized between any nucleus, the lone pair tends to occupy a lot of space. The lone pair electrons are not localized between any nucleus, and they extend to a great region. And as a result of that, the lone pair will then push the bond pair away, forcing the bond pair together because it's not localized between a nucleus. It is occupying a much greater region of space. So it will push the bond pair together to give itself more space, right? So what we are seeing is that any repulsion, because electrons are of the same charge, so any electrons repulsion that comes from lone pair tend to be stronger. So a lone pair repulsion, example in this case in water, a lone pair repulsion, these 2 lone pair pushing each other away, is very strong. And is much stronger than the push between the lone pair and bond pair here in blue. So the green repulsion is much greater than this repulsion between the lone pair and bond pair. And it is the lone pair bond pair repulsion and lone pair repulsion are all greater than the bond pair repulsion, which is the repulsion between these bonds. So as a result, we are seeing a very great force pushing them together. So this bond angle will therefore be compressed as a result of the push from the lone pair. We don't correct push, so we correct repulsion from the lone pair. So as a result of the repulsion from the lone pair, we will expect that the bond angle to be compressed. So if we look at this then, back to this diagram, then we will see that it originally is supposed to be 109.5, but this is going to give it a push down, compressing the angles, and we expect this angle now to be less than 109.5. But we are not allowed to write as less than 109.5. So in exam, if they ask for angle, you have to give a number. You have to give a number. And that number, general guide, is that for every lone pair, you just minus about 2 degrees to 2.5 degrees. So you have start off with 109.5. So I know I will be lesser now. I'm going to minus about 2 degrees. Maybe I'll just say 107.5. All right. If you want to minus 2.5 degrees, is also fine. So you just minus and then you get compressed. And then you know this is the new bond angle. Okay, I'm going to show you a few more later. Just give me a minute and I'll show you the animation so it's easier, okay? So now next I have CH3 minus. All right, okay, maybe we don't look at CH3 minus because it has the same shape as this. So let me look at something else. Maybe I look at maybe I look at this shape. Okay, if we have a shape which has 3 electron domains, for example, BCl3. So if I look at this, it has 3 electron regions, 1, 2, 3. So based on it, I will look for this. This is the electron geometry. It's the electron geometry. So the electron geometry is trigonal planar, is 120 degrees, is on a plane. Right? Now, and then what is the molecular geometry or the shape? Remember, the molecular geometry of or the shape is what you see after you cover up lone pairs. But in this case, there's no lone pair. So if there's no lone pair, what I will be seeing will be this again. So therefore, the molecular shape is also trigonal planar. Okay, do you understand? So basically, for shapes without lone pair, the electron geometry is equal to the molecular geometry because it's the same thing. There's nothing for you to cover up. And it's the shape. So that for shapes which has no lone pair, both are the same. So it is the shape. All right. What if I have what if I have BCl2 plus? If I have BCl2 plus, what if I have BCl2 minus? If I have BCl2 minus, maybe I will get a structure that looks like this when I draw the Lewis structure. Okay, boron has now, the total electrons has increased. So chlorine, 7 times 2, 14, plus 1, so we have 15. And boron will be 3. So 15 plus 3 will be 18. So if I finish drawing, I have drawn 16, 8, 8, 16. I left 2 and I give to the center here. Right? So this is the shape here. Now, in this shape, if I count the electron regions, is 1, 2, 3. So the electron geometry is still trigonal planar according to this diagram table, but the shape is not trigonal planar because I'm not able to see a lone pair, which is so tiny. So what I'm seeing, my eyes will be seeing this. So my eyes will be seeing a V-shaped or a bent shape. So the molecular geometry will be bent. The electron geometry is trigonal planar. Now, what about the bond angle? The bond angle starts from the electron geometry, which is 3. 1, 2, 3. So using 3, this is the starting. It should be 120 degrees. But because the structure has lone pair, and this lone pair is pushing, and as a result, this is going to be squeezed or compressed. So we expect it to be smaller than 120. But we are not allowed to write smaller than 120. You have to write a number. So, and a possible number you may write is maybe 118, 117. Anything that is logical. But so if you don't know what is logical, then for every lone pair, you minus 2 degrees. That is one way. All right. So with that, later we will go through this and then you will understand how to see the shape if you know how to draw. Okay, but before we go to that, we can look at the models over here. So this is a structure which has 2 electron domain. So you can see the best way to place these 2 as far apart as possible is to make it linear, right? And if there's no lone pair, then the shape will be the same as its electron geometry for shapes that has no lone pair because there's nothing for you to cover up. All right, what happens if it's a double bond? Now, if it's a double bond, the effect is the same. Whether it's a double bond or it's a single bond, is considered as one electron region or one electron domain. So you find that by changing just now the single bond into a double bond, it did not change anything. The angle is 180 degrees, or you can click this button to show the angle. All right. But it's not very accurate. This application is not very accurate when there's lone pairs. Now, what if there's 3 domains? Now I put in another one. So when I put in 3, I'm seeing 3 regions. 1, 2, 3. And so it's telling me place them as far apart as possible. If I have 3 things and place as far apart as possible, I should place them about 120 degrees apart. And therefore, the bond angle is 120 if there's no lone pair. Now, if there's a lone pair around, what will happen? So if I'm going to change one of the bond pair into a lone pair, so this is what I'm seeing. The electron geometry did not change because it's still 3 electron domains. It's still 3 electron regions. But the shape is different now. If I take a finger and cover this portion up and pretend that I'm not seeing it, what I'm seeing is this, a V shape or a bend shape, right? So therefore, the shape or the molecular geometry is bent. Now, the angle came from 120 degrees. But because the lone pair is not localized and occupies more space, it pushes this together. And as a result, this 120 will be compressed to maybe 118. All right, that's how you do your electron VSEPR. Now, so back to the notes. Why do we have to do VSEPR? And why do we need to know the shape? Because later we use the shape to determine the polarity. So again, the story starts from drawing the Lewis structure. Assuming that you have drawn Lewis structure and you know how to draw correctly, then you will count domains to find the electron geometry, the molecular geometry, and adjust the bond angle accordingly. So, okay, let's go through some examples over here. So, for example, if I have something like this, so I have central atom and electron pairs. I have 1, 2, 3, 4. 4. Bond pairs 3. Lone pair 1. Now, the electron geometry is tetrahedral. But the shape, after I cover up the lone pair and pretend that I can't see it, I'm seeing a trigonal pyramidal. Trigonal pyramid. And the angle will come from the tetrahedral but modified smaller. All right, let me show you tetrahedral. So if I'm going to show you a tetrahedral, it will look something like this. So a tetrahedral is now three-dimensional. So earlier on, when you have one domain and two domain, is planar, two-dimensional. This is three-dimensional. And because it's three-dimensional, so the angle is not 90 degrees. It's 109.5. And this shape is tetrahedral. All right. So how do you visualize a tetrahedral? You are visualize two on the same plane. These are on the same plane. And you are visualize something sticking out from the plane. And you will visualize something behind the plane. So it's three-dimensional. So as a result, the angle is not 90 but 109.5. Okay, so if we remove one and change it to a lone pair. So the angles are not very accurate, but let's say if we remove one and change it into a lone pair, you see the name of the shape. The name of the shape has changed. It's no longer tetrahedral, but trigonal pyramidal. So this is the shape. The molecular geometry is the shape. It's trigonal pyramidal because it looked like a triangle pyramid tapering upwards. Right? Now, if there's another lone pair, so if I have a structure that is two bond pair, two lone pair. So if I rearrange it, this is what I'm going to see. I will be seeing something like a V, right? A V shape. So you are seeing a V. So you can call it a V shape or you can call it bent. V shape is also correct. Right. Now, the angle will be quite different. If I have just one lone pair, this lone pair will push all of this downwards. And so the angle will now be smaller than 109.5. It will be 107. So about minus 2 degrees to 2.5 degrees per lone pair. Now, if I have two lone pair now, instead of one. So if I have two lone pair instead of one, like this. So again, it starts off from the 109.5 because that gives us the angle that we will modify from. So it starts off from 109.5. But now I have more lone pairs and I will be experiencing greater compression. So this has to be greater than, the compression has to be more than just now. So therefore, I cannot put it as 107.5 when there is one lone pair case. It's more extensive compression. So what happened is that since there's two lone pairs, you may want to minus 2 degrees, minus 2 degrees, or you minus 2.5, minus 2.5. So you will get about 105. If you start from 109.5, maybe you minus 2 degrees, 2 degrees, so you get 105.5. Okay? So that's how you come up with the bond angles for the VSEPR. All right, so that's how we work out the bond angles. So let's very quickly continue with this. So this one, can you change it? Can you just put a line instead of this? Okay, so in this structure, the central atom is N. There are 4 electron pairs, 4 bond pairs, and there's no lone pair. And the shape will therefore be tetrahedral because there's no lone pair. When there's no lone pair, we just follow the electron geometry as the shape, and the angle of tetrahedral is 109.5. Okay, now we will not do everything, we will skip a little bit. So if we look at this structure here, the central atom is C. There are 4 electron pairs, 1, 2, 3, 4, and out of this, there are 3 bond pairs, 1 lone pair. The electron geometry is tetrahedral, but the shape is not. Because if you cover up the lone pair, the shape will be trigonal pyramidal. And the angle will modify from a tetrahedral 109.5, and then you compress it to 107. Okay? So roughly, that's how you work out the shape and the angle. You can practice the rest on your own. All right? But I just want to do one more. What happens if there are two centers? So in this case, there are 2 centers, right? When there are 2 centers, then what do? We just look at one. Each time we will look at one. So you can look at this part first. So looking at this part, you can see the central atom is C. There are 1, 2, 3 electron regions. So 3. Out of the 3, all of them are bond pairs. So 3. No lone pairs. So for something which has 3 electron regions and there are no lone pairs, so what will be the arrangement? So you go back to this table, 3 no lone pairs, trigonal planar. So you will put down the shape around this carbon as trigonal planar, and the angle is 120 degrees. All right, so the takeaway from here is that even though you are seeing a double bond, you still treat as 1 electron region. Even though there are 2 center atoms, you do it one at a time. So you find out the shape with regards to this, then you find out the shape with respect to this separately. 2 different shapes, 2 different angles. All right. All right. Okay. So now we are going back to this part here a little bit. Now it's a little bit enrichment. So when the size, now these are all group 15. So we have nitrogen tiny, phosphorus bigger, AS even bigger. So what we are seeing in this enrichment example is that when the size of the central atom increases, the lone pair actually also becomes the amount of space it occupies also become bigger. All right. So what happened is that we also have the electronegativity. So the electronegativity of nitrogen is greater. So what we are seeing is that we will be seeing nitrogen being more electronegative will pull all the electrons to itself. So that's why if you look at the red dots, the nitrogen has a lot of electrons around itself. Imagine that it was the electron density. The phosphorus has lesser, the arsenic has even lesser because nitrogen is the most electronegative. So under these cases, what will happen is that there are a lot of electron regions here, right? And so therefore, you will see a very great repulsion in nitrogen. So you do notice a great repulsion between the lone pairs, the electron pairs of nitrogen. and therefore it will be able to push the bond pairs away, and then you get a smaller bond angle. So we can see that sometimes when you have a central atom that is more electronegative and it draws electrons to itself, it actually intensifies the electron repulsion here. And as a result, the angle will become bigger because these bond pairs are all repelling very strongly, and so the angles are bigger now. All right, so with that, I hope you know how to draw Lewis structures. We are not looking at the coordination bond first. I think we will do it the next lesson. So for this lesson, just make sure that you know how to draw Lewis structures. Okay, I will have to make sure that you know how to draw this, and I'll give you a list of other Lewis structures to practice. Okay, make sure you know how to draw all the Lewis structures over here also, because if you don't know how to draw, then you will have difficulty counting the electrons. Because if you draw wrongly, there's no way you can count the electron regions correctly. So for example, CH3, C will be 4 minus 1, will be 4. H will be 3 times 1, so 3, but you need minus 1 because of the plus. So left 2, so total 6 electrons. So with the 6 electrons, draw something first, and then check how many you have drawn. So take care of the surrounding first. Make sure they have stable configuration. If you are drawn 6, then you minus 6 left 0. That's it. That means this is the shape already, and square bracket and plus. Now, how in this case is less than an octet? There's nothing much you can do because you cannot do double bond, because hydrogen cannot form double bond, and you really have no more electrons. All right, that's why it's a cation. It's a little bit different. Okay, carbonate will look something like this. If you draw carbonate, one of the carbon is 4 electrons. There are 2 minus. So out of them, 2 of the oxygen has extra electrons. So they will have 7 electrons each. And one of the oxygen will have 6 electrons. So if you sum it up, it will be 24 electrons. So using 24 electrons, okay, first you draw your oxygen. All right, let's use a different color for the oxygen. So these 2 oxygen in yellow are the ones that has extra electrons. That's why they have the minus charge. So they have 7 electrons, and because they have 7 electrons, we just need to form one bond to make it 8. So then we will put in the electrons around it first. Now, then this oxygen in blue is the one that is from group 16. So it has 6 electrons. So usually they form double bond, 7, 8 to get 8, and then we draw and make sure it has octet, octet, octet first. So after ensuring that the surrounding atoms have octet, you minus what you have drawn in sets of 8. 1 set, 2 set, 3 sets of 8. So minus 24, I'm left with 0. So there is nothing to give to the center atom. That's the best you can do. Square bracket 2 minus, double check central atom whether it has an octet. So in this case, 2, 4, 6, 8. If it has less than an octet, then you will check whether it's one of the exceptions, whether it's the group 2, group 3, or whether it's a nitrogen. And if it's not, and if it yet is less than an octet, then try multiple bond. Okay, but in this case, it's an octet 2, 4, 6, 8, so there's no need to do anything. All right, so finish the drawing of the diagram and hope you can understand how to draw the Lewis structure and count electron domains. So you must remember this page. Must remember this table. If it's 2 domains with no lone pair, linear. 3 domains with no lone pair, trigonal planar, angle 120 first. If there's a lone pair, replace one of the sides with a dot, with the 2 dots, cover up, and what you see is bent. And the angle is compressed because of the repulsion. If you have 4 electron domains, now we are moving to 3-dimensional. So you'll get a tetrahedral with an angle 109.5. Replace any one with a lone pair, and as a result, what you are seeing is a triangle pyramid. If you still replace one more with lone pair, then what is left will be a V shape. So this is a case for 4 electron domains, 4 bond pair. This is a case for 4 electron domains, 3 bond pair, 1 lone pair. And this is for 4 electron domains, 2 bond pair, 2 lone pair. So we have all the different shapes here. Okay, and then use the VSEPR to work out the angle. All right, okay, so we'll stop here. Next lesson, we will continue from the dative bonds, the part that we have not done. That means, just a minute. So next lesson, which is the Friday HBL, we will look at the bond length, bond multiplicity, dative bonds, and then we will move on from here because we have covered all this already, and then we will look at the polarity. So we will be looking at how it affects the polarity.